the question on page 18, it says find the distance between the point and a plane. The plane in that question, it is given in Cartesian form. The plane itself is here somewhere. Here, that's the plane which you see in the plane which you see in that question. No, I think I'm mistaken. In the question on page 18, you're given the plane in the vector form like this. Here's the plane from the question 18, from the question on page 18. Yes. However, I would like to discuss with you what happens if you try to find a distance from the plane, from the point to a plane, when the plane is given in Cartesian form rather than the vector form. There are some differences which may speed up the process, and I want to discuss those particular differences with you right now. So I chose this example as far as I remember, and if I convert this plane to the Cartesian form straight away, I can follow the suit I just did on the previous slide. Well, it's here. Here's the normal vector, the determinant for the normal vector. Here it is. You don't have to copy that. It's not the focus of the current discussion. I just want to show you the Cartesian equation. And the result of this computation, again, if you follow the steps, that will be something like this. I will leave this for you to just fill in these gaps. It's not important right now for the current discussion. So if I use this normal vector, the corresponding Cartesian or point normal form for this plane will be here. Here it is. And that's what is actually important for us right now. So here's the 2, -2, and 1. These are the components of my normal vector we discovered via cross product. Here, -2, 0, 0. These are the components of my A vector from here. Here's the point normal form. If you expand the brackets, that will be the Cartesian form. You see how quickly you can find this Cartesian form via the cross product and point normal form. All right. Now, the question I want to address right now is this. The question is this: whether having the Cartesian form makes finding the distance from the point to a plane easier. That's the question I want to address. And in fact, it does, makes it easier. And I want to look into that. I want to look into that in the generality, in the full generality. So that's why I started with the general look of the Cartesian equation of the plane, or general look of the point normal equation of the plane. Where n here, the normal vector, obviously it's a vector which has these components, A, B, and C. Now the full setting, I explained the full setting. Now we can address that question. So on my diagram here, here's the vector A. I say here's the vector A. I didn't picture the vector itself. The idea behind the diagram is that this point, it's the tip of my vector A, which originates from the origin. And here's the tip of the vector B. Because if I picture the vectors, they will just clutter the diagram. I don't need that. I hope you can, with your graphics, with the most powerful graphics chips you have, you can imagine that. So we have a vector here, vector from the origin, and here's another vector from the origin, like this. Here's the joint perpendicular vector n, like this. From our general discussion on Tuesday, we know that the distance from the B point, from the tip of the vector B to my plane, is the expression like this. We have to project onto this n vector. We have to project this difference, B take A. If I project, it will be a vector whose length, or which length, will deliver me the distance. Here it is. That's what should I do? That is exactly what I should do computationally. I have to project this A, B take A, onto extension of n, or n vector. Let's just try to do that symbolically. So here's the expression for the projection. This one is the expression we have for the projection onto a vector, something we discovered with you last week when we discussed with you Cauchy-Schwarz inequality. So I just subbed in this expression. Again, I can cancel some things. If I cancel these things, that is the expression I will come up with. And that's the expression for the distance. On my previous slide, was it the previous slide? Yes, on my previous slide, I didn't use that formula. I left it for you to use that formula to finish it computationally, but we had this on the previous slide. What I would like to do now, I want to look into this formula further from the conceptual point of view. From the conceptual point of view, what happens here is this. Let me just assume that my B vector has the components x1, y1, and z1. If these are the components of my vector, then who can tell me what we're looking at here in the enumerator? In the enumerator, I can alternatively call this as point normal form of my plane, isn't it? I just replace my x here with the vector b. We all know, if I replace this x with the vector on the plane, it will be true identity, isn't it? If I replace it with the vector outside the plane, it no longer will be 0. But still, what happens here, I just replace this with the components of the vector b. Well, if I can replace it here, I can replace it here, isn't it? So what I'm saying is that the expression here in the enumerator is the left-hand side of my Cartesian equation of the plane, where I replaced x, y, and z with the components of the b vector. This replacement, it will not render this left-hand side 0, but it will give some number, and this number is sitting here. So I can write this like this. Here is the result of a substitution of my x, y, z with the components of the b vector. And in the denominator, we have the length of the vector n, which is, we know how to compute the length. It's the square root of the sum of the squares. I don't know if you're feeling the excitement right now, but you should. You should, because now you see how easy it makes, how easy the Cartesian equation of the plane makes the task of finding the distance from the point to a plane. All I have to do, I have to plug the point into the equation, and I have to normalize it by the coefficients like this. No projections, no dot products, no cross products, nothing. If you have the Cartesian equation of the plane, finding the distance from the point to that plane, it's like the things that you just compute. You don't have to think or just make any effort with your brain to finish this job. And that's the benefit of having the Cartesian equation. I hope you feel the same excitement as I do, even though I saw this many times before. So for instance, if I want to find the distance in the question on page 18, the point B is like this. It's 1, -2, -3. All I have to do, I have to put these numbers across this equation, and I have to, across the left-hand side of this equation, and I have to divide by the root of 4 plus 1, which is 9, and the root of that we all know is 3. So the distance is, did I do any computation? I didn't do any computations. I'll leave it for you to finish that. I can do it actually from top of my head. If I plug my vector in here, it will be 2 plus 4, so it's 6, plus 3, it's 9, take 4, it's 5, and divide by 3. So the distance will be, in the question on page 18, the distance will be, what did I say? 5 by 3, isn't it? 5 by 3.